Okay, so after the most difficult task of the conference, which is taking the picture, we can go back to our session. So we will start with the theory talk by Sakura Schafer-Nameki, who will talk about formal theory.
Hello, so thanks very much to the organizers. They have given me this very descriptive talk title of formal theory. Now, I am a theorist, so I know roughly what they might mean, but just to be clear, what actually is formal theory? So it's certainly not what I've erased here, so it's not something that you just disregard on HEP-TH. It's theory which tries to develop fundamental understanding of quantum field theories, quantum gravity, and really tries to consolidate many different tools from theoretical physics, all walks of life, and also mathematics. Of course, this comes at a price. Very often we'll have to do certain simplifications away from real-world problems, but we always strive to actually have some sort of avenue back to something that's more realistic. But you should keep that in mind for the whole talk. So this is going to be a biased selection. Biased because this is the number of papers on HEP-TH. So it's around 6,000, more than 6,000 papers. Roughly speaking, I have 25 minutes. But I'd like to actually start off with something that has dominated the parallel sessions, which are scattering amplitudes, and of course are very close to your heart as HEP-PH people and HEP-X people, so I'll just review this very briefly. But then there are three topics I'll focus on. One is, how does quantum gravity actually tell us about effects in the IR? How do we constrain our IR physics? Number two is holography, is sort of the gift that keeps on giving. And then finally, there's a sort of new development, which is called generalized or non-invertible symmetries. That's very close to my heart, which I'll tell you at the end about. Okay, so scattering amplitudes. We've heard many talks yesterday already that we'd like to have very high precision calculations for the LHC, in particular for Higgs production cross-sections, QCD plus electroweak. So we'd like to have higher loop, higher lengths, and this is sort of my understanding of what the current status of these calculations is. And so actually we'd like to develop tools to make these more precise, these computations. And of course, as formal theorists, we're not actually going to work in QCD directly, but things that are very closely related, are QCD-like. So for example, supersymmetric versions, n equals 4 super Young-Mills, etc. And they may not have direct phenomenological implications, but history has shown in the past years already that many computations we do there have implications upon actual QCD calculations. This is a list of topics that will feed into this whole amplitudes world, recursion relation, unitarity methods, whoops, the amplitude-hedron to get integrands, string amplitudes to actually do quantum gravity scattering problems, and then also applications to holography, of course. And then there's the double copy that's really going into actually calculating in gravity, so thinking of gravity as a Young-Mills squared. And there have been many talks on these, and shown in green in the parallel sessions. You should go and look at the slides for more details. And there's sort of this last piece, which is actually a drive to do computations at loop order, higher loop order, in any kind of colored theory. So that's something that's appeared very recently. Okay, but I'd like to actually talk about three other topics, as I said. So one is quantum gravity constraints on IR physics. So the traditional way that you must have heard before is string theory starts in 10 dimensions. We go down on some compact space on 6 space to 4 dimensions, get an effective field theory that could be the standard model plus X. X is maybe supersymmetry, some exotics. And so we define an effective field theory that depends on the 10-dimensional theory and the space M6. So it's this ping ball here. A more modern approach, which is bottom-up, is we just write down effective field theories, and then we ask, is this effective field theory actually embeddable into quantum gravity theory? That's question number one. And then question two is that quantum gravity theory actually realized in string theory? That's what we call string universality. There are many ways of sort of probing these type of effective field theories. There are many conjectures. I'm just highlighting 3. One is the distance conjecture. If you go an infinite amount of theory space, then you actually get a breakdown of your EFT, and you should get another EFT to describe that limit. The weak gravity conjecture, gravity is the weakest force always, and there are no global symmetries in quantum gravity. You have to be gauged or broken. So using these kind of conjectures, people have now narrowed down this sort of separation between things that are UV completable and things that are not. So that are not are in the swampland. Of course, doing this is not going to work directly in something like the standard model, etc. It's going to be in theories that are slightly more idealized. And just to give you sort of a hint what kind of idealization, these are 8-dimensional, 9-dimensional, abelian gauge theories with 16 supersymmetries. But in these kind of theories, people have now shown that you can make extremely precise statements. So this is our table, the rank of the dimension, the rank of the gauge group. The red ones are basically never UV completable. The green ones are UV completable, and those are precisely the ones that are realized in string theory. So this is actually showing string universality. The progress has been now pushing this down to 4 dimensions, exploring the space, and sharpening this difference between swampland and the landscape. And so this is sort of, at the moment, at the stage of sharpening the tools, but we can make extremely precise statements in this kind of realm. Now, supersymmetry is always the offensive thing in string theory construction. So what about no supersymmetry in string theory? It may come as a surprise to you that there are actually 10-dimensional, completely consistent, tachyon-free string theories. They're known since the 80s and 90s. There are 3 of these here. It's not important what they are, but they're non-supersymmetric and consistent. And in the past year, many people have started to look into these and sort of try to do more theoretical work, shown the uniqueness of some of them in heterotic context, shown the anomaly freeness of these, both local and global anomalies, and then actually studying sort of the standard things like moduli stabilization, compactifications, etc. So there's a real drive towards understanding non-supersymmetric string theory compactifications. Okay, topic number 2 is holography. So why is holography a theme that keeps coming back in this sort of dominating formal theory? Well, it's basically the setting where we have a gauge gravity duality. So actually, we would like to have them as equalities. And it's a strong weak coupling duality. So it allows us to actually study quantum gravity or strongly coupled QFT, depending on how you look at the problem. There's sort of this canonical holographic setting, which goes back to Malasena's work, which is the ADS-CFT correspondence. And here, string theory on a D+1 dimensional ADS space times some compact space is dual to a D-dimensional conformal field theory that lives on the boundary of this ADS space. And so this is really supposed to be understood as an equality. The parameters, so the conformal group are the isometries, but actually the parameters is string coupling, which is 1 over the number of colors. And then there's also sort of this alpha prime string quantum, which is dual to the Toft coupling of the gauge theory. And so the picture here is there's a string scattering inside string theory, so there's some string diagram, and on the boundary you interpret it as a correlation function in conformal field theory. The news here is these type of dualities have now really become precision computational settings. The ADS3-CFT2 theory correspondence in this particular background is now actually proven. So this correspondence exists, and you can calculate in all the regimes. The ADS5-CFT4 correspondence that you may be more familiar with, that's dual to this maximum supersymmetric Young-Milstein in 4 dimensions, that also has seen a lot of progress, extremely sort of sharp calculations of anomalous dimensions. But one of the really, really tricky things here is calculating in the string theory an ADS 5 times S5. That's extremely hard. It's a curved background with all kinds of fluxes turned on. But there's been interesting sort of progress in the past year illustrating how holography can actually teach us also how to do quantum gravity calculations. And I just want to illustrate this in this particular example of 4 graviton scattering in ADS5. So basically, you would write down all these string diagrams with these external string legs, and there are loops and string loops. And so this is really from the field theory 1 over n expansion. The tree-level term is already very complicated, and it has an expansion in this other parameter, which is like the Toft coupling. And so the leading term here is just a graviton scattering in flat space, and that's the famous Virasoro-Shapiro amplitude. I've written it down here as sort of a string worldsheet integral, and then there's subleading terms which are corrections into the ADS space. And now what people have done is narrowed down these terms and calculated them in some expansion using methods from the field theory. So using conformal bootstrap localization on the field theory side, integrability, and even number theory. So mathematics comes also into the game. So in fact, one can now write down this type of nice integral, which is very suggestive, looks like a string worldsheet integral, but now is actually the expansion in this 1 over r squared on the string worldsheet. So these kind of things can now hopefully be tested against some recent developments in string field theory, where you possibly can do calculations also in these ADS 5 times S 5 string theories. So what you should take away is ADS CFT in sort of this canonical original formulation is now really a precision lab for testing quantum gravity and strongly coupled conformal field theories, and there's been an enormous amount of progress. So there are other ways that holography plays a role. One interesting connection is to quantum info. There are sort of a few lessons. The first is that basically what we've learned in the last few years is that even simple quantum mechanical systems like spin chains, here's an example of a Majorana spin chain, this SYK spin chain, have emergent gravity. So if you take a large N limit, there are very sort of gravitational effects emerging. First of all, there's a center of charge for this, there's emergent conformal symmetry, and the entropy is basically akin to a black hole entropy. So quantum systems, even 1 plus 1 dimensional ones, have certain emergent gravitational effects. Of course, another interesting sort of connection is to the to quantum info concepts or to entanglement entropy. So one connection is that space-time emerges from quantum entanglement. Entanglement is important in testing holography, of course. And then we heard yesterday that also actually at Atlas they measured the top quark entanglement. So even in PH, HEP-X applications, these kind of quantum info concepts have come to life. Okay, so let me move on now to the third holography. This is basically a new kind of flat space holography. Instead of ADS spacetimes, so anti-de Sitter spacetimes, we're looking at holographic duals to flat space or asymptotically flat spaces. There are two approaches. One is called celestial holography. This is with an apology to Kepler for misusing his thing, but we're in Prague, so I thought I should at least have one of these. So celestial holography is basically saying you have asymptotic flat space-time, and that's dual to a two-dimensional conformal field theory that lives at null infinity. Carolian holography is also an asymptotic flat space-time, but there the dual field theory lives on squared plus and minus, but is a codimension 1. So in the 4-dimensional would be a 3-dimensional field theory. This is a peculiar field theory. It has a C goes to 0 limit. It's a very kind of strange causal structure that you get in these kind of field theories. So what actually can celestial holography do for us? It calculates, the key thing is, we can calculate scattering in flat space using sort of correlation function computations in this dual two-dimensional celestial field theory. So there's a precise map between these two things. There are symmetries, these are these asymptotic symmetries of flat space, these BMS symmetries, and they're realized in the conformal field theories and impose Ward identities, from which one can, for example, derive soft graviton theorems and also study the gravitational memory effect. The Carolian holography is a more peculiar kind of field theory limit that you find now on this null infinity here on this 3-dimensional boundary. Here C goes to 0. And again, there are these BMS symmetries. But the nice thing here is you can connect it directly to the standard ADS CFT holography. So there's now been lots of progress in the past year about limiting sort of ADS results and sort of thinking about a local flat patch in ADS, where you can then sort of do scattering in asymptotic flat space times using results from ADS CFT. So here the status is this is a very active field, but many open questions. So one really, really important question is what actually is this two-dimensional celestial conformal field theory, but it has lots of potential to actually tell us about quantum gravity in flat space, or asymptotically flat space. All right, so final topic. This is now finally something that I actually really strongly would like you to take on and really think about in terms of something extremely fundamental and new, which is symmetries, we all know, are extremely vital. So we know they organize the spectrum, interactions, the phases, SSB phases, and so on, and also anomalies. Usually we think about symmetries as groups. So we compose them, there's an inverse, and they act on point-like operators. And in the last few years, basically we've relaxed these two conditions here, and there are new symmetries that have emerged from that. The first thing is we can relax the action on point-like operators. And that's maybe not so new because you can always act on, say, a Wilson line operator in a gauge theory, and then it's known that there's a center symmetry of, say, an SUN gauge group, or there's a ZN center symmetry that acts on Wilson lines. The physics of this is, of course, the confinement can then be thought of as a symmetric phase for the one-form symmetry. So these things are called then one-form symmetries. The slightly more shocking thing that happened in the last 2 years is that there are symmetries which are not groups. So in fact, when you compose them, so if A and B are symmetry generators, they give a sum of other things that are also symmetry generators, some linear combinations. In particular, there's no inverse to this. So these so-called non-invertible symmetries, they're not exotic things. They're actually everywhere, in spin systems, but also in four-dimensional quantum field theories. And I'd like you to sort of just go back to a 1+1 dimensional model that you all know very well, the Ising model. It's just a spin model, spin up, spin down, a chain of length L. It has this very simple Hamiltonian that we can teach in QM1, sigma Z, sigma Z minus a coupling times sigma X. Now we can ask, well, there's a Z2 flip symmetry that flips all the spins. If I take G to 0, I have a ground state that's an ordered state with two states, so this is the symmetry breaking phase for Z2, and if you take G very large, we get a disordered phase, one ground state, and that's the symmetric phase. And of course, when G goes to 1, we get the critical Ising CFT. So this is the phase diagram of this particular spin model. There's a duality in the system which maps G to 1 over G, and this is a famous Kramers-Vannier duality. And basically, it just means we sort of map these operators in this way, but G goes to 1 over G is the actual action we realize in this way. And at G goes to 1, this actually becomes a symmetry. And this is now, if you compose this with itself, n squares to 1 plus the Z2 generator. And this is the simplest example of one of these non-invertible symmetries. So it's happening in this kind of 1+1D spin system. In the last 2 years, we've seen that exactly the same idea that I just explained in this 1+1D system, you can apply to four-dimensional gauge theories. If they have a duality, there can be a point in the parameter space where that duality becomes a symmetry, and in fact, these kind of things then become non-invertible, so they're not groups, symmetries of 4D gauge theories. Another very simple example is you take a U1 gauge theory in 4 dimensions, or in any dimension you like, and you gauge charge conjugation. Then the one-form symmetry of that will also become non-invertible. So basically, this is sort of a way of seeing this very quickly. But maybe for you, the most interesting case is when you look at QED with massless charge 1 Dirac fermions. We all know there's an ABJ anomaly for the axial current. This is not conserved. So D of this current star J is not 0, but is F squared. So it's not a symmetry generated by Noether's theorem. But we can actually now reinterpret this, put it into the symmetry generator. So this was the exponentiated symmetry generator. But now we dress it with some additional terms which precisely cancel this anomaly. So in this way, the ABG anomaly becomes actually a now non-invertible symmetry generator. And it's non-invertible because the n times n dagger becomes some non-trivial operator C. So this happens in sort of QED plus fermions and many other examples, many applications. At the moment, the sort of the bottom line of the applications at the moment are sort of reformulations of what we know from the ABG anomaly, but it's an extremely promising direction to pursue in the near future. I would like to spend a little bit of time explaining what the sort of hallmarks and the physics implications that are really non-trivial, and they really distinguish these types of symmetries from ordinary group symmetries are. The first thing is, how do they act on operators? So normally, you have a point operator, it's transforming in some representation under a group. If you take the Ising CFT, you take the spin operator, you pass it through this non-invertible guy, it becomes another operator called mu, and it's attached to a defect, a line defect, and this is a Z2 defect. So in fact, it maps order to disordered operators. And that's actually a very, very canonical effect of these non-invertible symmetries. Also in 4-dimensional SO3 super-Young mills, there are these non-invertibles, and basically the Whitney effect cannot then be understood as Toft loops. As you pass them through these non-invertibles, now become flux attached. The monopoles get charges under the electric charges, and so they get flux attached, again, ordered to disordered transition. So this is a hallmark of these non-invertible symmetries. Another nice implication is that non-invertible symmetries lead to modified crossing relations for S matrices. This has been shown very rigorously in 1+1 dimensional theories recently. So basically, they have non-invertible symmetries like the Ising model, for example, has. And if we actually study now the consistency relations of the S matrix, both the symmetries, integrability, unitarity, so these are integrable systems. There's a scattering of kinks, massive kinks in these vacuum A, B, C, D. And if we now actually look at the Ward identities for these non-invertible symmetries, they say the S matrix actually doesn't have standard crossing relations, but they're modified. So this non-invertible symmetry implies that the S matrix scattering, the scattering matrix has a different crossing relation. And so, in fact, this also is going to be important in 3+1 dimensional, for example, scattering massless fermions of dions. So here, basically, this is one actual implication that really non-trivially impacts the physics of these 1+1D systems, and hopefully also in higher dimensions. Another application is basically these non-invertible symmetries give new phases of matter. And that's happening in 1+1D, but also in 2+1 and also in 3+1D. So basically, they give new phases and new second-order phase transitions. And this sort of generalizes the standard Landau paradigm, where you have a group, a symmetry, and then you have SSB, spontaneous symmetry breaking phases. And then there are transitions between these phases, and there are the critical CFTs, like we've seen in the Z2 case that gave the Ising model. So the standard sort of paradigm relies on groups. And what we developed in the past year is basically taking these non-invertible symmetries and now asking what kind of phases do they give rise to, what are the gapped phases, the topological phases, and then what are the phase transitions. And this gives rise to sort of a new class of phases, phase transitions, and extremely nice sort of predictions also that can then be tested in the lattice. And just to sort of give you sort of a flavor of this, there's a simple sort of non-invertible symmetry, which is this called rep S3. The key has this non-invertible symmetry, E squared is 1 plus a Z2 generator plus E. And now we can write down all the phases for this non-invertible symmetry. There are 4 gapped phases. There are transitions. There are critical models. There's Ising, a Potts model, and an Ising plus Ising transition. And all these phases are connected, and they're all symmetric under this rep S3 symmetry. So there's an SSB phase, for example, for the symmetry. There's a trivial phase, a Z2 SSB, and so on. And this can now be confirmed with actual lattice models. You can write down a Hamiltonian as explicit as the Ising model with this non-invertible symmetry and actually test with numerics. And so now this can also be extended to higher dimensions, but maybe the most interesting thing is sort of the connection that these kind of models can now actually be put into some quantum experiment, like, for example, some cold atom experiment, where we can then model precisely the Hamiltonians that govern this phase diagram. Okay, so let me just summarize. Basically, formal theory, the status report is formal theory is very well and extremely active. There's lots of different areas of progress, amplitudes. Holography is extremely strongly going and has many implications. And then there are these new sort of emergent active fields, quantum gravity, constraints in effective field theory, but then also these generalized non-invertible symmetries that actually have implications in both condensed matter, but also in high energy physics. Okay, thanks very much.
Thank you for this very nice status report on formal theory. Questions?
There's a question there.
Hello. So thank you for a nice talk. So I want to ask you one thing. Can you formulate string theory in a cosmological background? Let's say in the de Sitter spacetime with quintessence.
Okay, that's a very specific question. I'm certainly not a model building person, but of course it always has been extremely challenging to do de Sitter. And there have been many debates, and I think the verdict is still out. Also, like, you know, in relation to the small planet, there are many conjectures which are being tested at the moment, but yeah.
Another question is like the recent developments in string theory can give a good insight towards the non-abelian gauge theories as well, to understanding of the non-abelian gauge theories as well?
String theory always has been good at getting non-abelian gauge theories, right? Even heterotic string theory has an E8 times E8, or SO spin 32 gauge group. The question is not, can we get non-abelian gauge groups? The question is, can we get non-abelian gauge groups that have then the right matter content, interactions, and so on? That's the challenge. Yes, there's another question there. There are many questions now.
So I have a question. You briefly talked about...
Where are you?
Here.
Oh, okay, yes.
You briefly talked about double cover. So my understanding of this is only very sporadic. But is it a way for eventual unification of gravity and
it's a way,
quantum chromodynamics, and with this maybe eventual unification of this unified theory and electroweak theory into grand unified theory?
So the double copy, which I think is what you're referring to, is a way of computing gravity scattering amplitudes and using results from scattering and gauge theory. And so that's been actually extremely active. People have done actual computations of scattering of gravitational waves, spinning black holes, all kinds of things using these methods. So it's, I think at the moment, a computational tool, but it's very much motivated from string theory because it's like a closed string, right, is sort of the closed sector would normally give rise to gravity. The open string sector would normally be the gauge sector. So in that sense, it's highly motivated from a string theory perspective.
Yes,
but it's not a unification mechanism, I think.
So the double copy, does it eventually can provide quantum gravity, or is it just a computational
Well, no, it
tool?
is. I think it is trying to compute, not just so it's trying to extend it to quantum effects. Yes.
Okay. Thank you very much.
There were questions here. Yes.
Yes.
Yeah, go ahead.
Thanks a lot for the nice presentation. When you discussed the non-invertible symmetries, you touched upon the ABJ anomaly, and in this context, you said this has applications for pion decay. So, and I was asking myself, what does it mean? I mean, is there any chance to learn something new about pion decay in this way?
Where is this? Here it is. There are some models which have a Z prime, and the Z prime also has a chiral anomaly, and basically this additional one. So that non-invertible symmetry can be broken, and it sort of is a small breaking of that symmetry, and that could give certain structures. Now, none of these models, and I think this is the key here, have yet predicted anything that hasn't been done in other ways. That's why it's a nice way of formulating things we know from ABJ anomaly. There are also some interesting applications to neutrino masses and so on, what we heard this morning. But all of these things aren't like bang on the money. They only come from these non-invertible symmetries. So it's at the moment a reformulation, but the fact that we have these symmetries is now being explored more broadly, and I believe certainly in many other directions, they would actually give us something that we might not have thought about in other ways.
Right, okay, but I mean, okay, learning something new is one thing, or getting something more in a more direct or
so you can think of basically certain models that have appeared elsewhere in terms of a symmetry breaking, which is a nice way of reformulating it, right? Usually the ABJ anomaly is sort of as there's no symmetry, right? Symmetry is anomalous. Now you can think of it as there's a symmetry, but it comes at the cost of being not a group, but a non-invertible symmetry. And so now you need to learn how to actually represent them, how they act on things, and so on. So it's a beautiful story. I don't want to sort of say it's not, but it's not giving you, particularly in this room, something that is a nice prediction at this point.
Thanks a lot.
Hitoshi,
we have a very short question. We have time just for one last.
Where's the question?
Thanks you for a very nice review. So, relaxing conditions sounds like something that mathematicians have been doing or should be doing. So I'm kind of curious whether these things were seen in math before or
relaxing which conditions?
Conditions on the group or the
symmetry.
symmetry.
Yeah, for sure, yes.
Like,
I mean, absolutely. I mean, it's probably the first time someone uses the word categorical at this conference series in its history of, I don't know, 70 years. That one relaxes this is actually what's called a fusion category. So this is a group. And you know, when groups came, it's a nice historical fact, when groups came into quantum mechanics, people were very averse to it. There was a thing called the Gruppenpest. People hated it and said, why should I study this? I think we're at the point where you need to learn about categories potentially. And I mean, it looks like an algebra, but actually there's a bit more structure, because in higher dimensions, you actually have extended operators acting on lines, surfaces, and then this becomes a higher category. But the mathematical structure, at least for 1 + 1D systems, exists. For higher categories, it does not, and it's being developed together with the QFT folks like us.
Thank you.
Okay, we have to finish now. We thank Sakura again.
Thanks very much.
Thank you. And we welcome Livia Soffi, who will talk about experimental overview of BSM searches.
Okay, thank you. Yes, so it's a pleasure to be here to give the overview of the experimental results on BSM searches at LAC. And let's break the ice just describing which are the 2 main approaches that we use at LAC to search for new physics. Either we perform refined measurements of the standard model quantities, or we directly search for rare and non-conventional processes. So far, we have observed some deviation from the standard model expectation. For example, here you can see a very nice high-mass DiGET event at ATV that CMS recorded during run 2. However, we do not have yet a conclusive answer for the existence of new physics, and for this reason, we are keeping taking data. In 2024, we have already collected more than 14 events femtobar, and the gain in luminosity, together with the new detector technology, are really boosting the capability of our searches as we get into the core of run 3. So in this table, I summarize all the new results that the Atlas and CMS collaboration have prepared for ICHEP. Each entry of this table shows you also the energy range that is explored. And you can see that the majority of the searches for this round focus at very low energy. In green, you see the results that I'm going to highlight, and I have chosen them because for each of them, I can give you an idea of the uniqueness of the analysis, just describing the most important aspect. Here in this table, you see that these results are grouped in terms of the model that is exploited in the interpretation of the analysis itself. And we have also addition to these models as a leptoquark or dark matter that you can find in the backup. However, in this talk, I would like to give you this overview, giving a different perspective. So for sure, I will highlight some of the results that are interpreted in the most renewed theories beyond the standard model. But I will also delve into non-standard strategies, signatures, or tools that are the key ingredients in our search for new physics at LAC. So let's start from a description of a few standard BSM searches. The first set of results apply to HDM, which is an extension of the Higgs sector that predicts the existence of 2 additional charged and 2 additional neutral boson to the one that we have already observed at low mass. In this context, Atlas searches for the production of a charged Higgs in the decay of the top quark, and the charged Higgs decays to CS. There was a lot of excitement for this channel because Atlas already observed an excess in a similar channel where the charged Higgs decays to CB. And this excess was around 130 GeV. This result with the decay in CS, however, does not confirm the excess around the same value of mass. CMS conversely searches for one of the heavy Higgs of the model in its decay to 2 big quarks. And the key aspect of this analysis is that by exploiting 2 completely different signature approaches, semi-leptonic or fully hadronic signatures, CMS is able to put sensitivity limits as a function of a wide range of masses, from 125 up to roughly 1.8 TeV. CMS searches also for the heavy pseudoscalar of the model, which decays to the Z and the standard model Higgs, and the Higgs in this case goes to 2 taus. In this case, the key ingredient of the analysis is the fact that CMS exploits a dedicated mass estimator, which is able to basically reconstruct the missing energy from the neutrinos in the final state and improve dramatically the resolution of the mass of the reconstructed A boson. You can see it in green. And this is very important because then this variable is the one that is used to discriminate the signal from the background in the analysis. It's also possible to extend this 2HDM model by adding an additional pseudoscalar that couples to dark matter. In this case, CMS performs 2 searches. The first one looks for the decay of the heavy pseudoscalar to the new pseudoscalar and the Higgs. The Higgs decays to 2 taus and recoils against the dark matter in the so-called mono-Higgs signature. The second result from CMS searches for the decay of the heavy neutral Higgs to the new pseudoscalar and a Z boson. This is a new signature at LHC that looks for dark matter produced in association with leptons and big quarks. This kind of process that comes from the fusion of 2 big quarks, it's really important because plays complementary sensitivity in the plane of the model of the parameter of the 2HDM at larger values of this parameter tangent beta, which is very important because it has an impact on the masses and on the coupling of the Higgs boson. Okay, so an alternative framework to extended Higgs sector is supersymmetry. We have already searched for supersymmetry chasing the most standard signature, but we didn't find it, so we had to be more creative. And CMS, in this case, searches for the so-called compressed supersymmetry scenarios, where the lightest supersymmetric particle in red has a very small mass splitting with respect to the lightest supersymmetric particle in green. This means that the products of this decay, shown here in blue, are very soft. Experimentally, this is a big challenge, and CMS has to circumvent this problem by developing a dedicated analysis categorization that exploits kinematic variables that are proportional to this very small mass splitting. One of these variables is shown here. On the left, you see the distribution of this variable for the signal, while on the right for the background. And you see that these 2 shapes are very different. This means that this variable is very powerful. And its usage, together with other variables, allows CMS to place limits on the mass of the supersymmetric particle, extending significantly with previous results, even at small values of the mass splitting. Finally, EV fermions. CMS and Atlas searches for heavy partner of the standard model leptons and quark. The first one is a search from Atlas that searches for heavy vector-like leptons. Also, in this case, the final state is very complicated. It has a lot of jets, big jets, and multiple tau hadronic decays, and exploits an approach based on a neural network to discriminate the signal. Also, in this case, there was a lot of excitement because CMS has an excess, but also in this case, the excess is not confirmed. CMS as well searches for the heavy partner of the top quark with the excited top decaying to a standard model top by radiating a gluon. And in this case, if you look at the limits of this analysis, CMS introduced a lot of novelties and has been able to improve the results with respect to the previous one, but also extend by a factor 2 the mass range explored. As I was saying at the beginning, sometimes we look for new physics without a specific model in mind, but we focus on very peculiar signatures, and to do that, we have to develop dedicated strategies in our analysis. So let me give you a couple of examples. The first one is the case of very merged objects, and this kind of signature happens when we have low mass boosted resonances. The first example is a search from Atlas that looks for low-mass boosted resonances decaying to dilepton pairs. In this case, these two leptons are very collimated and reconstructed as what Atlas called lepton jet. Atlas performed this analysis exploring the low-mass region, look below 20 GeV, and this is absolutely non-standard for LHC experiments. This is really great. And it's able to do this exercise exploring both the di-muon channel, but also the di-electron channel, reaching really very low masses. It's also possible to look for these boosted resonances in the hadronic final state, and this is a result again from Atlas that looks for exotic decays of the Higgs boson into two pseudoscalar. For low masses, this pseudoscalar is very boosted and decays to two very collimated B quarks. Atlas is able to build a dedicated algorithm to reconstruct the so-called double B quark jets at low PT. If you look at the sensitivity of the analysis as a function of the mass of this guy, you see that at very low mass, the category which has one of these merged B jet is the one that is the most sensitive, here shown in violet. This means that the machinery really works. Finally, also CMS searches for hadronic boosted resonances. This kind of signature happened because we assume the existence of the initial state radiation in the process, and this resonance can decay again, also in this case, to boosted quarks. In this case, CMS exploited an algorithm that is called particle net, based on machine learning, to discriminate the structure of two quarks inside the jet. And this algorithm is so good that it's also able to tell you if these quarks are a B quark or not. Thanks to this tool, I mean, we see that in these cases, for what concerns searches, machine learning really make the difference, especially when we need to develop object tools. CMS exploits, thanks to this, the mass of this jet and place limits that in the region between 50 and 300, shown here in green, are the most powerful one for this kind of signature. Okay, we can also look for less conventional signatures, and I'm going to highlight a couple of examples looking at the very high energy range or obviously long-lived particles, also with innovative analysis technique. So we have already searched for high mass dilepton resonances. We have already explored the high dilepton energy, but we didn't find anything. So also in this case, we have to make things a little bit more complex, and we are asking additional objects in the final state. We can do this in two ways. The first one, searching for a resonant production of two muons in association with B jets, and this is what CMS performed with these results that place limits up to 350 GeV and is complementary with another result already published at high mass. But we can also simply look at the dilepton production at very high mass, checking both the muon and the electron channel, and test the lepton flavor universality by comparing the dimuon and the dielectron spectra up to very high scale, roughly 1.6 TeV. Moving now to long-lived particles. So in this case, the key ingredient is the fact that we have amazing detectors, and we can use each layer of the detector in a complementary way to target specific lifetimes of our particles. So let me try to give you some examples starting from the tracker. This is the first run-tree result from Atlas in terms of searches, and looks for displaced leptons in the inner tracker. In this analysis, Atlas deployed several novelties that enhanced dramatically the sensitivity of the search. Just to give you an example, they started to use the large radius tracking, which is designed to increase the efficiency to displace tracks up to roughly 30 centimeters. You can see in this plot. For the very first time, Atlas uses the large radius tracking even at HLT level. And this gives you, if you want, an example of what really makes the difference for run-tree for searches. It's not really the increase in luminosity or in statistics, but more even important, the fact that we are now doing things that we were not doing, we couldn't do in the past. So thanks to these novelties, Atlas is able to extend the sensitivity of this analysis, not only thanks to the luminosity, but also exploring lifetimes that were not explored before. Moving to the calorimeters, also in this case, Atlas searches for long-lived particles that decays inside the calorimeters and exploit the information of the energy deposited inside the calorimeters. In this case, there is a clever strategy. Atlas basically asks the presence of an additional object in the event that can be two jets or an electroweak boson. And in this way, they can use this object to trigger, and they can enhance significantly the sensitivity to the phase space of the long-lived particle signature. Thanks to this strategy, Atlas is able to place limits that are a factor 3 better with respect to previous results with the same luminosity. And finally, reaching the muon detectors, CMS searches for decays of long-lived particles to photons. These photons reach the muon chambers in CMS. They interact with the steel shielding material of the chambers, and they produce high multiplicity hits. These hits are clustered and called the muon detection shower. This is really interesting because it gives you an example of an innovative usage of a detector that in principle is a muon detector, but is effectively used as a sampling calorimeter. Okay, the last section of my talk concerns tools. We also have dedicated tools that we learned also from our colleagues that do not look for some BSM searches, but then we exploit them. I'm not going to talk with machine learning because there is a talk later in the afternoon by Javier, but I'm going to give you a couple of examples that gives you an idea of how we try to increase the likelihood to look for new signals at trigger level in order to do not miss potential new physics hints already in the online selection. The first example is scouting. So we talked a lot about scouting yesterday. I just summarized here in a tweet that basically the idea behind scouting is that we reduce by a factor 100 the size of our data, and in this case we can increase the rate, or if you want, we can save data in kinematic regions that were not accessible before. In run 2, we used, in terms of searches, we used scouting to do simple things, dimuon or dijet searches. And already with the dimuon, CMS has been able to reach very low masses and perform results that are compatible with dedicated experiments. In run 3, we did a step forward. We took all the information that are inside the scouting data set, and we used them to build elaborated objects. For example, tau leptons decaying hadronically. We tested the procedure with simulation. We obviously used only the information available in the scouting data set, but we managed also to modify the reconstruction algorithm in order to increase the efficiency up to very low value of the hadronic tau, up to 5 GeV. With this algorithm in place, we also wanted to test it in data, and we started by reconstructing the Z2 tau resonance using 22 and 23 data. This is a starting point, but gives you an idea of how many things now that one can do exploiting also more elaborated objects in the scouting data set. And let me finish here with the trigger. During run 3, both CMS and Atlas have developed a dedicated program of triggers dedicated to long-lived particles, and they already deployed them. This is an example where Atlas exploits the energy deposited in the pixel detector to identify new heavy charged particles, and you can see that the variable trigger level nicely matches with the variable at offline level. Conversely, CMS deployed a dedicated displaced jet tagger in the trigger. And the plot here shows you that this new trigger in run 3 brings a factor up to 10 in terms of improvements on signal efficiency with respect to run 2. And this has been already used for a physics results at CMS. Okay, I am approaching my conclusions. I would like to leave you with some hints and expectation for the future. So I asked myself what people attending ICHEP 2024 will find in their light cone concerning BSM searches. For sure, there is run 3. Run 3 is already bringing us a lot of data. We have higher energy, increased luminosity, we have our improved detector, and we are already analyzing this data. We have some excess that we are chasing. For them, we do not have yet a run 3 result out. For example, searches at low mass in the diphoton channel, or, as I was saying at the beginning, very high digit searches. Going even further, Illumi LAC will bring a huge gain in terms of luminosity, but this is not the end of the story. Illumi LAC is also bringing new detector and new detector capabilities. And just to give you an example, we will be able to use the new timing detectors to look for long-lived particles in a way that is completely new with respect to what we have done in the past. Okay, so from run 3 to Illumi, we are entering in an era of exploration for new physics. And the next few years will promise a wealth of new knowledge. Optimistically, we are expecting to exceed the expectation. Okay, with this I conclude. I thank you for the attention, and I leave here all the results that unfortunately I couldn't cover today.
Thanks a lot for this nice experimental overview. Questions to Livia?
Yeah. Hi. Thanks for this nice overview. About the anomalies and run 3, what is the general strategy? Are you, Atlas and CMS, will they take the full run 3 data and then look for these anomalies, or are they going for the first year already and try to see whether there's something there? Is there a common strategy? How is this handled?
So I think that the strategy is common because it's based on physics motivation, obviously. So it cannot be the same for all the accesses that we have because they are different entity of accesses. I can tell you that a general guide principle for us is the fact that we need to collect at least the luminosity that we need to give the same sensitivity that we had in run 2 to whatever excess we had, and eventually also plan to combine. And this can, based on the sensitivity that we reach on the specific excess, can force us to wait or to go public immediately.
So you will at least accumulate something like 114 versus femtobarn and then do it again?
Not necessarily. Some other analysis can use also less than this luminosity, but can have other, let's say, aspect to control as to the quality of the objects and so on. Yeah.
Okay, thanks.
Any other question? I don't see. Okay, I don't see any other questions here. So we thank Livia again.
Okay, we move on. So we move from experiment to theory, and Stefania will tell us about theoretical insights into new physics.
All right, thank you very much. Thanks for the invitation. So theoretical insights into new physics. So the quest for new physics, we don't know what the next new physics scale will be. If nature has new particles at or above the TeV scale, then we know that we need experiments with high energy. Otherwise, if new particles are light below the electroweak scale, we know that we don't need necessarily experiments with high energy, but we need high intensity and precision experiments. Now, we have seen an enormous progress in the exploration of new physics in the past decade or so, but numerous gaps need still to be covered. In particular, the most hidden particles are what we call dark sector particles. With this, I don't mean necessarily only dark matter, but any new particle that is not charged under the standard model gauge symmetries. These new particles can still interact with us. We can write down some interactions, some portals between the dark sector and the visible standard model sector. And through these interactions, we can search for these new particles. Now, to make these searches, we also need some theoretical guidance. We don't have a guaranteed discovery anymore, but dark particles can help us in addressing some of the most pressing open problems in particle physics. In fact, we could have sterile neutrinos, as we have already heard, to build models for neutrino mass generation. We can have new dark scalars, both in supersymmetry or neutral naturalness models to ameliorate the hierarchy problem. We could have axions addressing the strong CP problem, and so on and so forth. And for this talk, what I want to present are theories for dark sectors and experimental strategies, focusing in particular on search gaps. First, we'll discuss those dark particles that can arise at electroweak scale or above, and then we'll focus on the sub-GeV scale. We'll go through several experiments, including high-energy colliders, meson factories, as well as fixed target experiments. So let's start with electroweak scale dark particles. Now, we can produce dark particles at LHC because generically they will mix with standard model particles. In particular, if we have a dark photon, the dark photon can mix with a hypercharged gauge boson of the standard model. A dark scalar can mix with the Higgs of the standard model, or sterile neutrinos can mix with the neutrinos of the standard model. So it's important to have resonant searches in a mass range as broad as possible to search for these particles. Of course, if we want to have access to relatively low masses, we can use search strategies like data scouting, as we have heard, or we can utilize ISR. And here I'm reporting a beautiful plot from the LHCb collaboration that shows the measurement of the dimuon spectrum. And perhaps if we have, for example, a dark photon, this could show up here in this spectrum. Now, in addition to searches for resonances, we know that oftentimes dark particles lead to exotic signatures. So, for example, collimated objects or exotic jet structures coming from dark QCD models. So in this sense, to look for these particles, we need to be creative and design new search strategies, especially in this context of dark QCD models. Now, in addition to the production of single resonances, it's important to keep in mind that the presence of dark sectors can modify the phenomenology of SUSY models as well. In fact, there are extended SUSY models like the NMSSM that do contain a dark sector. The NMSSM has an additional singlet chiral superfield on top of the particle content of the MSSM. And then these additional particles, this additional dark scalar, pseudoscalar neutralino can lead to new signatures if compared to the signatures that we can get in the MSSM. So let me give you an example as taken from this relatively recent paper. So let's consider an MSSM model in which we have a singlino at the bottom of the SUSY spectrum. And this singlino is co-annihilating with other particles like either a Higgsino or a Bino. In this first case, we get a spectrum that is squeezed. In fact, we have the chargino as well as the three lightest neutralinos that are close in mass. And because of this squeezing, we are suppressing the most searched decay modes for the electroweak sector of supersymmetric theories. And we are opening up instead other decay modes containing photons. So at the end of the day, we'll have signatures like this containing one or more photons, one lepton or jets plus missing energy. However, these objects here are relatively soft because of the squeezing, so we might need an ISR jet, and this leads to new signatures that we could look for at the LHC. In principle, we could have also more than one photon, as we can see here from this line. So plenty of new searches that we can get in these models, these SUSY models where we have a dark sector. All right. Now, in addition to the modification of SUSY signatures, dark sector models lead oftentimes to displaced particles, so long-lived particles. In fact, new physics particles can have a width that is suppressed by many different reasons, depending on the model. So we can have a suppression because of small mass splitting. This is what happens, for example, in SUSY, if we have a V node that is the only light particles and all the rest of the SUSY spectrum is decoupled. Then we can have a suppression of the width because of a high new physics scale, and this is what happened for glue balls in twin Higgs models. Or we can have multiple suppressions, as it happens for sterile neutrinos, whose width is suppressed by multi-body final states, as well as a high new physics scale eventually. So plenty of motivations to look for long-lived particles, and as we have already heard, we have many searches. But we have also appreciable gaps. Here I'm listing some of them. In particular, we have gaps in the search for long-lived particles at low mass, or long-lived particles coming from Higgs decays, singly produced, or displaced taus. So a lot of more searches can be done in the future by the LHC. And here I wanted to give an example coming from long-lived particles coming from Higgs decays. So in this plot here, this was a summary plot that we did for this paper a couple of years ago, putting together Atlas CMS and LHCb searches for a Higgs decaying to 2 long-lived particles. And here you can see the bound on the Branchy ratio for the Higgs going to 2 scalars as a function of the lifetime of the scalar. And what you can see is that we have many orders of magnitude that we are covering in the lifetime, and this is pretty remarkable. Future searches will really benefit from the luminosity, because these are typically searches with low level of backgrounds. And also, we expect to have significant improvement because of better search strategies, and eventually also better trigger strategies. So in this context, what I want to mention is that so far, most of the searches are done requiring one or more displaced objects, displaced particles, and it would be interesting to see searches for one displaced particle plus additional object in the final state, and this could be either missing energy or some visible particle. And this could arise from this decay topology like this, where the Higgs decay to 2 different particles, where they can be both long-lived or only one long-lived and one prompt, and so on and so forth. Okay. These type of signatures can be obtained in twin Higgs scenarios. So in twin Higgs models, the Higgs can decay back to the twin sector that typically can contain light particles, lighter than the mass of the Higgs boson. There are several analyses for the Higgs decaying to light glue balls. So here you can see the spectrum of glue balls in a pure SU3 theory, so in a theory where you don't have light dark quarks. And these signatures are interesting because they lead automatically to displaced particles, because these lightest glue balls typically decay in a displaced manner to standard model fermions. And then it will be interesting also to study more complex signatures, like the Higgs decaying to the lightest glue ball plus an additional heavier glue ball. Heavier glue balls are typically more long-lived, so they can be invisible in our detectors. And it will be interesting to study this set of signatures. And tools have been developed, actually, for doing this. So there have been the development of Parton shower and hadronization of dark QCD theories. So we have now the tools to fully investigate these type of theories. All right. So what about sub-GeV dark particles? So first of all, I wanted to motivate why we are interested in models that contain sub-GeV dark particles. So let's go back to our new physics scale, the unknown, and let's place famous models. So let's place the QCD axion, WIMP dark matter, sterile neutrinos, responsible of seesaw. And here what I want to mention is that we can extend these ideas in the sub-GeV range. So yesterday we have heard about the possibility of having light dark matter. And here what is interesting is that we can reuse the idea of WIMP, the idea of thermal freeze-out, and extend it to the sub-GeV range. It can still work, but we need to add a dark sector, so we need to add additional interactions of dark matter in order to have to obtain the measured Rayleigh abundance generically. Also, in this context, I can mention that we can extend the QCD axion models towards heavier masses. We can still address the strong CP problem with heavier axions in extended QCD sectors. And this is also very interesting because these models typically can more easily address the axion quality problem, having a heavier axion and lower decay constants. Also, we can take sterile neutrinos for the neutrino mass generation and keep them lighter. And this is what happened, as we have heard this morning, in the inverse or linear seesaw models. So there are plenty of motivations for considering new particles in the sub-GeV range. Okay? And then the question is how to probe these particles. And one possibility is to use, indeed, meson factories. What is promising here is that we expect to have a jump in luminosity in the coming years. This is shown by this number, so I'm collecting the number of pions, kaons, and B mesons that we have already produced and will be producing in the future. Some of these experiments are not yet approved, like the Pioneer experiment, but you can see that this will be the next generation of Pion experiments. And in addition to these meson factories, there are actually other experiments that will be producing a lot of mesons, and this, as we know, is the LHC and future colliders, as well as proton fixed target experiments. Here I'm bringing up two examples, one for Fermilab, the DarkWest experiment, and one for CERN, the SHIP experiment, with the corresponding number of mesons that they will be producing. And we see that we have really huge statistics. So how to use these huge statistics to probe light particles? So let's start with sterile neutrinos. So sterile neutrinos could be produced from meson decays. And here I'm reporting a summary of the parameter space that we were already able to probe in the past, these gray regions, for a sterile neutrino that is mixing with the electron neutrino of the standard model. And we see also what we expect in future years. And we see that a lot more parameter space will be probed in the future, sometimes pushing the bound on the mixing angle by 1 or 2 orders of magnitude. What is important to notice, though, is that most of these searches or projections have been done under the assumption that sterile neutrinos decay visibly to the standard model. What if sterile neutrinos are invisible? They might decay to neutrinos, they might decay to dark matter. There are much fewer studies for this possibility, so it will be interesting to see what meson factories will say in this respect. And just to give an example, here I'm reporting a possible search, a model-independent search for a sterile neutrino that is invisible. The sterile neutrino could be searched for at B factories, produced from tau decays. The idea is pretty simple. So tau decays can give us a sterile neutrino plus a 3-prong hadronic final state. We don't care of the sterile neutrino, but we measure as accurately as possible this hadronic final state. And the kinematic of this will be affected by the presence of the sterile neutrino. So depending on the mass of the sterile neutrino, this hadronic final state will have a different energy or a different invariant mass. And then fitting these observables, we can set a bound or eventually discover a sterile neutrino. So this was first proposed in this theory paper, and then relatively recently there was a Babar search that explored the new region of parameter space, and it will be interesting to see what BEL2, especially with a full luminosity, will be able to say. Then the last topic is what about axion-like particles. So I argue that axion-like particles that are much heavier than the QCD axion can still address the strong CP problem. And then the question is, how do they interact with us? So the goal would be to probe as much as possible the EFT that we can write down for a CP-odd pseudoscalar with a Lagrangian that has an approximate shift symmetry. And these are the terms that I can write down, so the coupling of the axion-like particles with gauge bosons as well as with the fermions of the standard model. And we can have access to all these operators at different experiments, either high energy, low energy flavor experiments, a fixed target, as well as meson factories. And I want to give you a couple of examples. In fact, there are already a lot of investigations for searching for axion-like particles from meson decays. Searches and also theory investigations focused mainly on these flavor changing neutral current decays. And these decays are a natural prediction of a lot of axion-like particles models. For example, if you have an ALP that couples to W or the top quark, then you can induce at one loop this flavor violating coupling, and therefore these decays. Much less attention has been dedicated to these charged current decays that we can see here. And this can also be predicted in ALP models. So let me again give you an example. If you take an ALP that couples mainly to electrons, then this is your Lagrangian. You can write it in a different way where you have the ALP couples to a derivative of a current. You can see the standard vertex, the interaction of the ALP with two electrons. But you can also see that you generate the coupling of the ALP with a W, an electron, and a neutrino. This is generated in theories that break SU2, because otherwise this combination of couplings would be 0. And these models are interesting because phenomenologically, they predict an enhancement of these charged current decays. So looking for these decays, we might be able to probe a lot of new regions of parameter space. And this is what is shown in this plot. So in gray, you can see the regions that were already probed in the past by past experiments looking for neutral currents. And the several colored regions are instead regions that we can have access looking for charged current decays. And some of these decays have not been looked for yet. For example, we can search for a kaon decay to an electron, a neutrino, and an ALP, where the ALP decays to a +, or even a W boson exotic decay decaying in the same way. So for example, if we search for this W exotic decay, and we are able to set a bound at a level of 10 to the -5 on the branch ratio, then we'll be able to probe all this region above this line. Okay? So again, once more, several searches have not been done yet, and that will be interesting to probe new models for axion-like particles. Now, in this last, maybe skip this. In this last slide, what I wanted to point out is that, as we already mentioned, proton fixed target experiments will produce a lot of mesons. So how to use those mesons to look for dark particles? So the overall idea is simple, namely we have these experiments that are starting with a high-intensity proton beam scattered against a dump. And because of this many scattering, we can produce a dark particle. This dark particle can be long-lived, and then it can simply go through the dump, and then decay back to the standard model after the dump, and then we can search for these visible decay products in a detector downstream. And there are many searches that can be performed in the coming years. I'm taking as an example these two experiments, one at Fermilab, one proposed experiment at DarkWest, and one at CERN, the ICHEP experiment. And here we can see that there is plenty of regions of parameter space that can be probed, either for a dark photon or a dark scalar. And these particles can indeed be produced from meson decays at these experiments. All right. So this leads to my conclusions. So in this talk, I wanted to argue that dark sector particles, namely those particles that are not charged under the standard model gauge symmetries, are a typical prediction of many new physics models that address open problems in particle physics. There are a lot of searches, but numerous gaps in the experimental exploration. And the LHC will have many opportunities to test these theories, looking for exotics, soft objects, displaced particles, also new SUSY signatures. And meson factories and fixed target experiments will be complementary, exploring the sub-GeV range. Thank you.
Thank you for this very broad overview of theoretical insights. So the floor is open for questions.
Thank you for this nice rendition of things. But I was trying to understand. You didn't mention any kind of information we might get from the astrophysical side of things on this dark sector. At least I didn't understand very much that you said very much about that. Could you say something about that?
Yeah, no, that's a great question. So this was because of the topic that I was assigned to, and there is a lot to cover. But definitely, I mean, when you go in the sub-GeV range, there are a lot of bounds coming from astrophysics and cosmology. What I can mention, I mean, in the plots, there were some of these of the bounds. For example, here you see the bounds from supernovae, or there are bounds from CMB when you are at light mass. So there is a lot of complementarity between accelerator probes and what you can do in astrophysics and cosmology. This complementarity is, of course, model dependent, but definitely once that one study sub-GeV models, so new physics models with sub-GeV particles, one has to really ask the question that you asked.
Other questions?
Over here. Yes. Thank you, very nice talk. I wanted to pick up on what you said on the long-lived searches. You can add objects. I think in general, once you have zero background, it doesn't make sense, but I agree it would be great to further explore how we can use that in triggers especially.
Right. Yeah, definitely. Yeah. So in triggers, and also depending on the exact search, sometimes one can have a little bit of background, and this can help. But I fully agree with your comment.
Thank you.
And this is also a question, especially for the high luminosity LHC, when you will have a lot more data, then this will become more relevant than now. Yeah.
Not see other questions.
Yeah,
If not,
there is one there.
Okay, sorry.
Yeah, I have a question on page 9. So again, on the long-lived particle. So as seen earlier this year, BESS3 discovered a gluon-like particle at 2.3 GeV. I wonder if it can enter this decay you mentioned, and especially you say heavier gluon will be invisible. I wonder 2.3 GeV, what will that look like in this decay?
So in general, yes. For these twin Higgs models, typically glue bores are a little bit heavier than that. It depends really on the parameter space and what your dark QCD, what is the confinement scale. But typically, they're a little bit heavier than that, like in the 10, 20 GeV mass range or so. But this is a good question. It should be investigated. But yeah, there are also other theories that are more easily predicting even lighter particles, if you want. Yeah.
Thank you.
Any other question? If not, we thank again the speaker. And we have the next speaker, Sergei Nagaitsev, which will talk us about collider present facilities, accelerator facilities, and future and approved facilities.
Hello, everyone. Can you hear me? Okay, so the title of my talk today is Present and Approved Accelerator Facilities. It's a bit generic, as you can see. And as you may imagine, it's not so simple to summarize in a compressed 25-minute presentation all of the present and approved accelerator facilities, even classifying or deciding which ones to include and which ones not to include. Of course, required some, creative thinking on my part. So let's start by, I think, trying to summarize how I would classify particle physics accelerator facilities, and I broke them into 3 groups. First, of course, many people, of course, know that we'll be talking about colliders, whether it's lepton or hadron colliders. Then I grouped them into high-intensity accelerators, which, of course, not only focused on developing high-intensity beams, but also very specialized beam targets that operate in very extreme environments due to radiation and thermal shocks produced by these high-intensity beams. And the third group, I would call it specialty beams that are one-off type of experiments, such as, for example, an experiment shown here, coming online sometimes in 2026, called the Mu2E experiment at Fermilab. Typically, those do not require very high-intensity beams. They operate in so-called slow extraction regimes, and they could, not always, but so they are specialty, one-off type, such as mu on G-2, the proton electron dipole moment measurements, or antiprotons. Okay, so I got lots of help from my accelerator colleagues around the world. So you can see that this is a team effort to create this talk, to describe where we stand in various facilities around the world. And because I'm going to run out of time, I'm going to put the summary up front for you to give you the key messages. So when the music starts playing at the end, and and I didn't finish the talk, so you know what the key outcome of this is. So first of all, I have to tell you that as an accelerator physicist, I've enjoyed this long-term productive partnership between you, particle physicists, and us, accelerator physicists, for many years. You continue to challenge us on the accelerator side by developing new ideas in physics, by putting new requirements on accelerators, which leads us to deliver these interesting new facilities and new accelerator physics ideas. An example, of course, is for the approved, since I'm talking about the present and approved facilities, what are we focusing on right now as an accelerator science and technology team? In colliders, we are mostly focused on achieving the highest average luminosity. It's, of course, the peak luminosity is important, but sometimes it's not highly desirable because of various limitations on the detector side. Of course, so on colliders, we are focused on achieving the highest average luminosity through reliable operations and continuous implementation of various technology and physics innovations, such as nanobeam, crab wastes, crab cavities, various coatings in order to suppress, for example, the electron cloud effects. On high-intensity beams, there are now 4 facilities that joined the 1 megawatt club. I will tell this a little bit more in detail later, but mostly the particle physics high-intensity beams are focused on delivering beams for neutrino experiments and developing these specialty high-intensity beam targets. Okay, so let's start with colliders. Colliders, as you may know, have a very long history in our field, starting with the first collider in 1964, Ada. There has been many colliders since then. At present, there are 7 operational colliders, 5 electron-positron colliders, 2 hadron colliders, and there are 2 approved colliders which are under construction, NICA and the EIC at my own lab, Brookhaven National Lab. So, of course, the most important consideration for colliders has been historically the energy reach, but not only. Now the energy reach has shifted also to the luminosity frontier because we are struggling to get to the highest energy, and you know how much effort worldwide it's taking for us to develop, for example, the next energy frontier machine, the FCC. Of course, everything is driven by, ultimately, by the costs, reliability, and flexibility, and energy efficiency at the end. So let's dive into the present and approved colliders that we have now in the world. So first of all, if I look at the historical plots of colliders by plotting the energy versus time and peak luminosity versus time, you can see that hadron, the colliders recently, except for the LHC, have stopped being the energy frontier colliders, but rather luminosity frontier colliders, where the highest luminosity is being pushed by the B factory, super KEK B at KK. So on the lepton, in the lepton collider family, we have 5 colliders, starting from the lowest, and I would call them factories, because each one is focused on a specific energy, center of mass energy range, starting from the lowest, Daphne in Italy, working in the Phi meson center of mass energy around 1 GeV, followed by Web 2000 in Butker Institute, which has the center of mass energy of about 2 GeV, which allows for it to observe hadronic production, for example, pairs of neutron-antineutron from electron-positron collisions, and so forth. Following by BEPC2 in Beijing, focusing on tau charm, Web4M at Butker Institute, again, focusing on Upsilon meson. And finally, Super KEK B is our flagship highest luminosity collider, focusing on the B meson energy range. So Daphne has just completed a very successful run, physics run, delivering 1.5 inverse femtobars of data to Siddharth-2 experiment. Now, of course, the question is, what is the next for the Daphne accelerator collider in the future? We are, as a community of accelerator physicists, discussing how to incorporate Daphne collider into the studying physics problems and innovation technologies, perhaps focusing on the next generation of colliders such as FCC-EE, testing various collision concepts, and of course implementing short-term experiments for particle physics. So this is what the team at Daphne has been focusing on developing a plan on what to do with Daphne. Of course, we know that Daphne has produced 2 very important accelerator physics innovations. One of them is a long-range beam compensation with external wires to compensate the beam lifetime. And secondly, the so-called crab waste, which increased the luminosity by about 60%. This crab waste is now implemented in Super KEK B. Okay, so now at Butker Institute, we have 2 colliders, and the most interesting, in my opinion, of course, is the collider Web 2000, operating with approximately 2 GeV center of mass energy, which has recently provided data for hadronic corrections to the muon G-2 experiment performed at Fermilab. So you could see on the archive the paper and also threshold measurements of neutron, anti-neutron pair production from electron-positron collisions. Okay, so now talking a little bit more about BEPSI-2. This is a collider in Beijing that also can be configured as a light source. Of course, this has been in operation already for more than 15 years, achieving the luminosity goal of 1 × 10⁻³ inverse centimeters per second, which in an energy range of roughly 2 GeV. So the highest luminosity was achieved at about 2 GeV per beam, so 4 GeV center of mass energy. And the question, of course, is now what's next for BEPSI? Well, they are undergoing now an upgrade, which would extend the luminosity reach of roughly 1 × 10⁻³ to an energy range from 2 to 2.5, so from 4 to 5 GeV center of mass. And the commissioning would start in January of next year, 2025. So now let's switch to the Super KEK-B design. Of course, this was envisioned as a machine which would increase the luminosity of a previous machine, KEK-B factory, by a factor of 40, using the technology such as nanobeams or in tiny, extremely small vertical beam sizes, which you can see here. It's the record squeeze beam at the IP implemented in Super KEK-B, the so-called large Pivinsky angle. Okay, I will, if someone is interested, I can tell you later. And of course, implementing the crab waste developed at Daphne. The Super KEK-B factory just fits into the Tsukuba campus. As you can see, you cannot spare any more room on the campus. So this encompasses 2 rings, the high-energy electron ring at 7 GeV and the low-energy ring at 4 GeV, operating in a B-meson type energy range. So so after some 2-year shutdown to implement the BEL-2 detector upgrades and Super KEK-B accelerator upgrades, leading to nanobeams and very large collision angles at the collision point, we are now seeing luminosity increase by about a factor of 2.5 compared to KEK-B. Of course, it's nowhere near to what was promised of a factor of 40. So one of the challenges that the team at Super KEK-B is faced with, and a very serious obstacle to achieving high luminosity, are the so-called sudden beam loss events. These are events that in which the beam is lost literally in 2 turns. We are still, as a community, not quite sure what causes those type of events, where you can see that the beam suddenly, the vertical beam size, which is so essential for luminosity, starts to increase rapidly, immediately losing luminosity. And the suspect at the moment is dust particles that perhaps fall down from the vacuum chamber into the beam and create an immediate effect of luminosity degradation. So a couple of words on colliders. Hadron colliders. Okay, there are, of course, RIC, LHC, and EIC and NICA, 2 colliders under construction. So if you are curious, go to the talk posted on Indico, and you can see the evolution of luminosities through the years since the first collider in roughly 1972 up to today, including the projected luminosity for the EIC. So let's start, of course, with the LHC accelerator complex. which is underpinned by the technology, engineering, and research and development in accelerators, including various superconducting magnets, power circuits, innovative RF devices, and beam screens. So this is all the underpinning, of course, of the present reliability of the LHC accelerator complex, the high LUMI upgrades, which are, again, underpinned by the technology development and even the future options for the LHC, for CERN. So in the LHC operations, we now see that we've exceeded the peak luminosity goal designed by a factor of 2. We don't want to push it any higher because of the pile-up in the detector, so the team at CERN is implementing the luminosity leveling, so to keep the pile-up constant. And what you can see here is the luminosity is now quite flat. But of course, the delivered luminosity is going to be up about 100 inverse femtobarns this year. So the high luminosity, high LUMI LHC installation is going to happen between 2026 and 2028 for 3 years. And of course, from then both the accelerators and the detectors will be upgraded to accommodate a higher peak luminosity of about 5 times 10 to the 34. Okay, so now one word about the relativistic heavy ion collider, which is at my home lab. This is home for a collider which is operated now for 25 years and will shut down in 2025. This is focused on collisions of ion species from polarized protons to the heaviest beams of uranium, with 2 detectors recently installed as Phoenix detector in operations since 2023. And so we are now in the last 2 years of operation with many species of ions in collisions. Of course, we cannot compare RIC and LHC directly, apart from the proton-proton collisions, which at RIC are at much lower energy, roughly 270 on 270 GeV. Finally, this is what I'm personally working on, the next machine that will replace RIC, which is the collider in the RIC tunnel, where we are going to replace one of the RIC hadron rings with an electron storage ring, trying to achieve the luminosity a factor of at least 100 higher than what was achieved at Hera in DESY, by adding several electron rings, the electron storage ring and the electron rapid cycling synchrotron. Okay, finally, NICA accelerator complex is ready for commissioning and will likely start commissioning at the end of in the first half of 2025. So just a few words about high-intensity machines. Of course, the high-intensity beam power being the most important parameter here can be simply characterized as the number of particles per beam or per bunch, per pulse, times the rate, times the energy. So that gives you power. Okay, so this roughly, you can split it into 2 groups. This is where accelerator physics is, and this is how much money you want to spend. You can, the rate is typically set by the design, and it takes a lot of money to change both the rate and the beam energy. Of course, the beam energy is chosen for a particular physics goal, and here you can see the 3 types of high-intensity machines, such as cyclotrons, Linux, and rings. The record beam power now belongs to a spallation neutron source facility at Oak Ridge in the US at 1.7 megawatts, achieved just recently in July of 2024. But as I told you, there are now 4 facilities that have joined the 1 megawatt club, starting with PSI quite some time ago, and of course Oak Ridge SNS, J Park, RCS at 1 megawatt, as well as what I'm about to show to you is the CERN, is the Fermilab machine, have just recently achieved 1 megawatt by tweaking slightly, by increasing the ramp rate of the main injector, by decreasing the time that takes to ramp the machine up to the highest energy and down. Okay, so just maybe a couple more, 1 or 2 more minutes to finish my talk. So, of course, the highest efficiency machines at high intensity are the cyclotrons, because they operate with a fixed magnetic field and low RF frequency, which can be made, 50 megahertz or so that can be made quite efficient, quite high efficiency machines. So this is the highest efficiency machine at 1.4 megawatts is the PSI, which also, of course, gives beam for one of the particle physics experiment, mu-2,3e. JParc is a machine that is a joint project between KK for particle physics as well as Japan Atomic Energy Agency. And the RCES has just recently reached the 1 megawatt beam operation. On the main ring side, which is dedicated to particle physics, of course, we have the about 800 kilowatts right now, and trying to achieve 1 megawatt for Hyper-K by 2028. And on the slow extraction side, the progress is steady toward achieving slow extraction at 100 kilowatt level. This affects, of course, particle physics such as kaon experiments, COTO, and things like that. Okay, so the Fermilab accelerator complex has now achieved 1 megawatt for neutrinos and 80 kilowatts for short baseline neutrinos, as well as beams for in the future for mu-2e. I will mention one slide on CERN. Well, of course, most of the protons, as we know, do not go to the LHC. Most of the protons produced by the LHC injection complex goes to other low energy users. The LHC takes the tiniest fraction of proton beams. So you can see a list of many facilities that are operated by the LHC injector complex, including some of the exotic production of P-bars, here shown ELENA and AD, for example. In summary, the present accelerator and approved facilities have 7 colliders, 5 electron-positron and 2 hadron colliders. The 2 colliders under construction are the Brookhaven Electron 9 collider, which is aiming to exceed Hera luminosity by a factor of 100, as well as NICA. Present high-intensity machines have now, there are now 4 facilities that joined the 1 megawatt club. And of course, on the particle physics side, the focus is on delivering the highest beam power for neutrinos, and on synergies with other applications such as neutron spallation sources, nuclear physics, as well as accelerator-driven systems. And with that, I'll finish my talk.
Thank you very much. Thank you, Sergei, for this impressive amount of information that would stay on Indigo, so we can pick up from Indigo. So, questions?
Yes. Could you return to slide 8, please? Slide 8.
8, yes. Yes?
Yes, that's it. I was wondering where SPEAR is on that. SPEAR? You remember SPEAR?
Yes.
Well, SPEAR
these are operating machines.
Is Where, right there, there is sphere.
Yes, it's
Yes.
buried in
It's
that
been
book.
gone for, I mean, this is in history books already.
But
Yes,
on this
so my title of the talk, if you remember, is Present and Approved. So this is what I've tried to put into my talk, is that what we have on our plate today as accelerator physicists, and maybe a couple glimpses into what we are constructing right now. So yes, I fully respect SPEAR. I have nothing against SPEAR.
Well, could you just show me slide 8 again, please?
There is no SPEAR here because it's not an operational facility. These are the 5 colliders that are in operation today. So with the Daphne just completed the run right now, and then these are all the machines that we as accelerator scientists worry about, and think, this is what is the present suite of facilities in the world working on particle physics.
There is a question here.
Yes.
Okay. In general, for the collider, you have more than one experiment, but Bell, it was known that we cannot have these two detectors. But EIC, is there any restriction from your accelerator point of view that the more than one experiment cannot be put there?
In which machine?
EIC.
No, EIC is going to have 2 experimental regions. Okay. We are funding, our present funding limits our design to a single detector. But there is, the EIC has the second IR as part of the design. We have a fully developed interaction region in the second IR.
Okay, that's fine. Okay.
Yes, I can show to you even the location. So this is the detector we are constructing in the first phase, and then will come later.
No, so I see only one detector usually talk. Why not people are talking other detectors? In general,
yes, if the community would like to have the second detector, please form. I mean, I'm responsible for delivering the accelerator. Okay. I would like to, if there is, people around the world that would like to, form a collaboration and develop this.
You need to bring the luggage with the money.
Yeah.
We have another question there.
Yes. So when you mentioned the list of approved facilities, it looks to me a little bit too short. So you somehow mentioned the Nika facility in Russia and somehow didn't mention the sister facility in Fiery, Germany, which is under active construction right now, and probably approved facility in China at the same energy range.
Yes. So. I realize that I've missed some of the nuclear physics facilities because this is a high-energy particle conference. The reason why I chose to mention all of the colliders is because the number of colliders is so small, and this community of colliders is, tiny. And I would say it was a choice made because I couldn't fit all the if you start going with more and more nuclear physics facilities, then you would have to include various cyclotrons, various Van de Graaff accelerators. I mean, the list would go on and on. Sorry, again, I've made some choices, and the collider community is so small that I've chosen to put all the colliders because it's just there are only a handful of them.
Okay, other questions? Okay, one over there.
So in the EIC, you're using injected polarized electrons. Can you use Sokolov-Chernoff electrons there?
Yeah, Sokolov-Chernoff effect is very important at highest electron energy, 18 GeV, where so one of the main physics questions for the electron ion collider is the origin of spin, or measurement of spin-dependent cross sections, where we would like to compare cross-sections with spin forward and spin backwards for electrons, changing the beams on a short time scale. So I would say at the lowest energy, 5 GeV, which is still of interest to many users, it is very difficult to use Sokolov-Ternov. At 18 GeV, it's actually a nuisance for us because it leads to depolarization of one of the spins faster than another, or so faster than so I would say yes, but we are not relying on it. In the design, we are relying on a polarized electron source from the cathode.
And the lifetime of the source is?
It's been already demonstrated. It's an electrostatic high-voltage electron gun, and we've run it already for weeks. So it's a good, it's a gallium arsenide specially designed cathode with polarized, using polarized laser to produce polarized beams of high current, roughly 11 nanocoulombs per bunch. Sorry?
You said the photocathode would last weeks then?
Last many weeks. Okay. I can give you data. I can show it to you.
Okay, I will stop here because we are running late. So we thank all the speakers of the session.
Thank you.